for many years when I was living in Boston, I always live in an apartment. And usually I like to live in an apartment, this top floor on the corner, so that nobody really bother you. And so in the past, basically every Halloween, so we just buy a few bag of small candies, you just give it to the neighbors. And now we live in a house which basically is open to the street. And I think each year has a lot of kids coming in, which is really fun. And I can't believe myself actually just spent $50 to buy candies from Costco. It's a huge bag of candies. So anyhow, tonight everybody will encrypt their face, right? So it's just like normally we encrypt our data. Last time we went through a very rapid lecture, namely we mentioned 3 protocols in one shot, right? Because we are entering that stage. And so today and in the next few lectures, I will essentially focus upon many facets of one basic things that are called zero-knowledge proof. So the book we use does not have chapters on zero-knowledge proof. As a result, I mailed a handout last time. And so I will mostly try to contain my lecture according to the handout. With, sometimes I will go beyond a little bit. Okay? So today I would like to mostly focus upon one aspect of zero-knowledge proof. It's called interactive proof. And in which way such a schema eventually become an important components, largely to security and crypto. Okay. So interactive proof actually arises in several directions. Some came from crypto, and some actually just come from complexity theory. And it is a sort of new way to combine few of the classical concepts together. One is mathematical proof, which we have been learning as a kid what should be considered as a good proof. And secondly, is a complexity notion of what you can do or what you cannot do in a feasible time or with feasible resource. And third is randomization. Right. So you can see those components are, to a large degree, all the facets of what we teach in crypto anyway, right? Because a good crypto system should come with proof of security, not just correctness. And randomization essentially is everywhere in crypto, right? We are trying to creating pseudo-randomness. And the complexity theory, other sort of basis allow us to overcome the paradox of what someone can do and someone cannot. Right? So essentially, to a certain degree, it's not surprising that this become part of the common thread that eventually combine. But one of the earliest motivation of such a proof system is what we already know, used typically in ATM machine or when we try to log on to the computer. And both of these applications essentially build upon a notion called identification problem. Right? How do we identify ourselves to a system that we can log in? How do two machines identify with each other? And how do we somehow get on this device to get the money out? Right? So those are fairly commonly showed up in essentially our daily life, particularly ATM machine. Right? ATM machine essentially has been there throughout of modern cryptography. Right? And from movies, novels to real life, people knew this is not the perfect system. Sometimes money gets stolen because of certain ID was forged or some other aspect of digital secrecy was leaked. Right? So what is this identification problem? If you really think about it, it gives a little bit of sense of proof. Right? Give a little bit of sense of proof. You have this ATM machine, or you have a computer somewhere, and you have a user who want to identify him or herself to the machine. Right? This user could be a machine as well. Right? So essentially, if you really think about it, such a system also goes through a basic generation protocol. Right? So before we can talk about this machine and user interact, there's first some common ground that they interact. Namely, at the beginning, in the generation protocol, they need to generate what should be agreed upon as a certificate for the user to for identification. Right? So in common days, for example, computer, for a very long time, it's just password. Right? For a very long time, it's just password. That is, at the beginning, the user and ATM machine agree upon a secret code. So this is almost nothing different from symmetric key encryption, right? They agree upon a secret code, right? And so associated with secret code is the user's name, right? So the machine basically will remember this name and the code. Sometimes we call it password. And the user just remember the code, since the user knows its name. Right? And so name probably is public, because that's sometimes you cannot quite protect, but the code is not. Right? So that's why before we somehow use heavily that the password, because it's generated inside a private, almost like secret key encryption system, that this knowledge of the code somehow provide as identification of the user. And this is how we log on to computers. And this is also partially why to have this secret code that is difficult to guess is important. And to a larger degree, most of our systems ask us to, after a few months, try to regenerate our password. I think most of the time we get quite annoyed, right? Because it's a problem that after a while, we just don't remember our password anymore, right? And clearly other system has been produced. For example, use a fingerprint, use like biometrics, or some kind of image recognition of eyes and facial recognition. So those are also other elements fundamentally are used potentially as identification, right? So for example, if we watch a lot of different movies or TV program, I used to run on electric trainers and watching Nikita. So they often have this certain different way to open a door, either through by fingerprint or looking at certain things or some other combination of code, right? And so, but mathematically, they actually follow very similar schema, right? That is, there is something which we try to say after generation, after the interaction, it is hard to break, right? Hard to break. So this clearly didn't pass the first assumption of crypto. That is, all other communication are public, right? So which means that when a user needs to log on to ATM machine, there's no way to guarantee that the passcode you type in is not discovered by somebody else. There could be camera monitoring, there could be some other device, machine learning, just learn from the speed you hit the key card, and so on, right? So this communication, it's never been clear whether it's secure or not. right? So that's why make traditional authentication harder. Is that if you give out your password, you give out your password, and if this channel of communication is insecure, it is insecure. You give out your password, right? Stolen password is a very, very common phenomenon, right? So this is really the profound challenge of this identification problem. That is, to a large degree, we want to say that this channel is insecure, right? So if you look at it to a large degree, public key encryption also offers some solution technically, right? One way to log in to such a system is to use public key. That's one actually possible way to do login, right? That is, before you need to log in, the ATM machine will ask you for a name, and what is stored here is the public key of the user. So then, to a certain degree, ATM machine can choose a random message, encrypted, right? So it can choose a random message, encrypted, and ask the user to decrypt. So you can say, in principle, public key system is powerful, right? So it provides, to a certain degree, another alternative solutions, right? That is, when you try to log on to the machine, the first thing you type in your name, and the machine may just come out to say, here's the challenge, decode it, right? So then, if you decode it, you will send it back to say, your original message is this, and if correct, the machine lets you in, otherwise, reject, right? So you can see that public key encryption, to a larger degree, is fundamental, right? It's not just for communication. It can be used for identification, right? And in our hand, this is much better than password system, right? Your password you give out. But public key system, that as long as you hold your encryption, a decryption key, and in some sense, public key system provides such possibilities, right? So this is actually a schema of what I call interactive proof for identification, right? So this is a schema for interactive proof of identification. You can say user, an ATM machine, and the user will initially send name, and the ATM machine send a challenge, and the user send back a decryption of this, and then ATMs will say m prime is equal to m, accept, m prime is not equal to m, reject. Right. So this, to a large degree, is what we call public key revolution. Right? It's actually, as we see from last class, provided some mechanism to do digital signature. And in this particular setting, it provides some schema to perform essentially identification, right? And but to a larger degree, it does introduce a certain notion of interactive proof as just fundamental schema, right? So what other form of interactive proof showed up? So when public key is encryption created, led by RSA, and so clearly, as we mentioned, that this theory began to advance pseudo-random number generation, right? Pseudo-random number. So the right of public key encryption system and their function often are the building block for pseudo-random number generation. And so this also arises to the time that we have to deal with human sometimes interact with machine, right? So this human machine so human-machine interaction system, in some sense, asking for much practical solutions. Because if you look at this encryption schema, we can't do it, right? Can you decrypt your own message in your head? It is non-trivial, unless we have some other device to help us to do it. And if you lose that device, you also lose it, right? But the schema, nevertheless, is a powerful schema, allow you to do identification, particularly between machine and machine, right? Because when one machine needs to contact the other machine to log in, it has sufficient power to do some encryption and decryptions. Then this does provide a very robust identification schema, right? So namely, that as long as the host knew is a public key and private key pair are properly generated. That is somehow certified that is a proper set of public key and private key pair, right? And so in the middle of 90s, it became much more clear that there's more people may break into the system if you just use standard password. So back then, gosh, I don't remember what's my first password, how long it is. 6 letters or numbers. It was so short back then. You know, and that's at the USC. So I used to have a login name, STENG. And I think when I came back, that login I technically can still have, but somehow they couldn't assign it back to me. So that's why my USC email now called Shang-Hua at USC.edu. And yeah, it must be very short. But my passcode does become longer.
It has to be longer, very long.
Huh?
It has to be very long in USC, like super long.
Yeah, back then they have no constraint. They just basically say, put in your password. And this password, I think, just few digits at that time, just maybe 6 digits. And in the bank, ATM machine, any of you use 10 digits?
No. 4. 4 at the
Look at that.
4.
You use 14 digits? You have good memory. You're young.
You mean on the ATM or like
ATM machine.
ATM?
Oh no, I
Only
think
4. Only
I
4.
think you only have to.
You have to use only 4, right?
Only 4.
I mean, this is crazy if you really think about it. Only 4, right? That's a standard one, right? That's my memory.
Yeah, it has to be 4.
I think in China it's 6. That's often messed up my.
More people do.
Yeah, when I go, yeah, they have more people, so they need the 6 potentially, and so this basically in the 90s, there's a company called Digital Dynamic. Okay, so this after there's a company called RSA. Okay, there's a company called RSA, and our professor Edelman is among one of the founders. And so then here rises digital dynamics. This is during what they call VLSI days. So namely, finally people are able to make VLSI chip small enough so that they can essentially create a chip at that time roughly half this size. So, so this company has one patent to start. The patent actually is they patent some practical version of pseudo-random number generation. Okay, but particularly a practical involving the pseudo-random number generation. So here is their schema. So I'm trying to motivate. Eventually, you can look. It's almost like another interactive proof schema. So they said is that when the user created an account on a machine. Okay? Not only they will agree upon a password for the user to use login, but also they actually agree upon, just like symmetric key encryption, a private key between them. Okay, a private key. So it's code and there's a private key. So let's call it R, little r. Okay, a private key. So it's remember the code and little r. So this user will have this digital device, and this card will be coded with R and with a pseudo-random number generator. That every minute it will put a new number, I think 10 digits at that time, if I remember correctly. I may still have one of such cards in 10 digits, then it is showed up here. So then in order to log in, it will go with a system that is his name, and then basically it will give a password. So this is just like standard thing, and then so this one doesn't have a reverse query, and then it will look up the card in the next prompt to enter these 10 digits on that card. Okay? So the machine sometimes say reject, enter another digits, because sometimes as the minutes goes by, they may get confused which number is which number. Right? So that's why they actually just ask one more time. If one more time you couldn't get it right, then it will be rejected. Right? So what happened is that their server essentially just continue to run the pseudo-random number generators. Right? So this generator to continue to produce long string. Every minute there's a 1. Right? So then basically this card doing nothing else. It just produce. It just implement the pseudo-random number generators. And then basically if this number synchronize match what's the number in the machine, it will be accepted. Okay? So that was one of the early attempts to use the modern cryptographic techniques to somehow assist this human-machine interaction. Because it's recognized human couldn't do much, and the password system could be defect, because people can easily steal the password.
But this is used still, right?
This is used. Okay, so this occurred in '94 or ish, and they're brilliant. Tell you how brilliant they are. They convinced the government that all government computers should have such a thing first. So they made enough money that a lot of high-tech industry began to have this. The first time I got such a card, this is much earlier. This is probably '92. The first time I got such a card is that I was consulting for a company called the Thinking Machine Corporation. They produce high-performance computers out in Cambridge. So this is right by the river out in Cambridge. And Thinking Machine Corporation so eventually, their product eventually embedded into many other systems. The company eventually folded. So this one of the most glamorous moments is that they produced this parallel computer has about 1024 machine processor in it, and it's selling very well. It's built upon a hypercube, and it's very beautifully designed, artistically packaged. That when they produced the movie called Jurassic Park, at the beginning there's a scene that they got the DNA of dinosaur, and then this parallel machine tried to number crunching to reconstruct, and that is one of the Thinking Machine Corporation, CM5, is actually producing that. So it prominently put this machine in one of the most popular movies of its time. So this company at that time quickly implemented just such protocol. I remember even as a consultant, I was issued one of these cards, and I was curious to ask them, how much does this card cost? He said $60. So I said, this is $60? So soon, this company bought RC. So the company is not built upon which idea is mathematically profound, but it's really about which idea somehow produce a lot of revenues. Right? So this company actually, so this is how RC is first time was sold. So then this company eventually folded it multiple times into other companies. Okay? But what I'm trying to use this to illustrate is this notion of interactive proof become very natural because this fundamental problem of identification. Right? So somehow, one agent needs to convince the other agent, he or she is what they claim to be. Right? And in the digital world, it's basically set up as a mathematical formulation. That is, I know certain secrets that we agreed upon, and hopefully nobody else knows. Right? So mostly it's use this schema to provide at least what we consider to be identification system. Okay? So I would like to basically for now slightly detach this ATM thing. I will come back. Essentially say that this investigation of interactive proof eventually lead to much more than what it just tried to solve this particular problem. But it did provide mathematically a perfect solution to identification, right? So we have been talking about pseudo-random number generation, encryption, secret sharing, and this basically, I personally feel is the first time that the crypto moved beyond just communication, right? It's really become an integrated component for computation as well, right? So where's the other place interactive proof showed up? Interactive proof showed up also in society for many other ways. So in fact, it's one of the basic premises to relook at what is NP as a complexity class. So this is sort of complexity theoretical view of interactions. Okay, so in NP class, we are dealing with a problem that is also very close to identification. It's very close to identification. So this is a mathematician's version of what genuinely mathematical identification that only they can play and nobody else, right? So what they say is that, so what is NP problem? I think the easiest example is 3 sets, right? So we're giving a 3 sets formula, which typically is phi equal to, a bunch of and with a bunch of ors. Right? A bunch of ors of variable that either in the positive or negative form. Right? So as a 3-set problem, the computational version, which means the decision version, is that upon receiving this description, this input, we want to know whether there exist assignments, namely the assignment of x, this vector of x1 to xn, x1 to xn. So whether we want to assign it either to 0 or 1, or true or false, to make this whole formula to be true. Right? So this usually write as a function formula of phi of x1. Right? So that's why xi can take either positive or negative in logic. And as a decision problem, we're asking whether there exists an assignment that makes this formula true. Okay. So one version of identification problem by formula is that you know you agree upon a formula that you know a solution, and when you need to log in, you need to offer the solution to the variables, and the machine is evaluating to see whether it's true or false. Right? So you can see generically this is what the machine do anyway, right? You're evaluating something to see whether equal or not. Right? We are evaluating to see whether equal or not. This can be recoded as a 3-set. Right? So you can see this schema, to a large degree, is a 3-set problem that is somehow trapered out with a public key notion. Right? So the traditional NP complexity can be loosely viewed as a problem between a prover and a verifier. So it can be viewed as an interaction between prover and verifiers. That is, they commonly know an expression called phi. In this interaction, the prover will offer an assignment right? The verifier will reply, either accept or reject. Right? So this depends upon whether phi of x1, xn is equal to 1. Right? If equal to 1, accept. If not equal to 1, to reject. So this is a very simple mechanism if you want to draw a picture of what is NP. Right? So when we define NP, how do we define? It's just such a problem that what do you need? You need this verifier to be polynomial time. Right? The verifier is polynomial time. If the verifier is a polynomial time machine, then this schema basically defines what our traditionally called NP. I have to bend the map myself in a different way. I can't quite bend down to figure it out. Right? So you can see this is where complexity theory tangled with a somewhat an interactive schema. Right? Okay? So one basic way to relate this logic to the computational class is basically say that a problem is in NP if there exists such a protocol such that, one, it has what we call soundness, and secondly, we have completeness. Right? The completeness means that if phi belongs to 3 sets, namely phi is satisfiable, then there's ways to make the verifier accept. Right? This implies verify. There are interactions to make the verifier accept. If 3 sets has a solution, because this is all-powerful machine, and this is a polynomial time machine. So, if it's satisfiable, the all-powerful machine can find the solution, send over, and it will make this polynomial time machine to say yes. Right? So this is the notion of completeness in the traditional mathematical logic. Right? That is, if this formula is satisfiable, then there's one way for prover to convince the verifier to say yes. It only say one way, right? It didn't say prover can do whatever to convince it. That's just, it's just prover can convince. Okay? So what is soundness? Soundness means that if phi is not in 3 sets, there's no way that the prover can convince the verifier to accept. No way for so this is the traditional view of NP completeness. So one way to define NP class in this language is that a description of problem that has the following sort of protocol, or a language has a following L belong to NP. If L has the following property, then it has an interactive proof of this nature to have the soundness and the completeness. Then this defines exactly what NP is. Right? You can see it's a schematic, right? But this is what I call an interactive view of NP. Right? It's literally, if you can design such a protocol, upon receiving a common input, a prover say I talk, it talk, then the verifier look at what the message say I accept or I reject. And if this schema satisfies the soundness and the completeness, it means that this language belongs to this proof system. And technically, if this language belongs to this proof system, it belongs to what we traditionally call the decision problem that is part of NP. Okay? So in some sense, NP has essentially one round interaction, right? Where the prover send, verifier reject. Just this one round interaction. Okay? But interaction is also part of a system deeply. So where do we usually have interaction? We play games, board game. We play chess. That is a much more complex interaction, right? So remember, what is a board game? Or play chess? Is that you have 2 players. You can prove, first player can try to prove I can win. The second player try to say you can't beat me, right? So then basically taking turns, the first player will offer a data, the second player will offer a data, and if they go beyond the rule of the play, then immediately the other player say you lost, right? Because you can't go beyond what is allowed to play. Otherwise, we just do this thing, and there's a particular moment, one of the player just stood up and congratulate the other player, so you're winning. Right? So that is a much deeper interactive proof. There's a much deeper interactive proof. So in fact, there's a complexity class. There's a complexity class called P-space. Those decision problems, those language can be recognized in polynomial space. It's precisely characterized by a multiple polynomial round of interactions. So what is P-space? P-space, again, it has a prover, and you have verifier. So what P-space usually signifies, it signifies the following mathematical formulas. That exists x1 for all x2, exists x3 for all x4. that phi is true. This formula. This is what the mathematician or complexity theoretician called the ultimate interactive board game. The ultimate board game is that I give you a formula with n variables. The first player can choose a variable. The second player can assign second variable. The first player assigns third variable, and so on. So the first player assigns all the alternate variables, and the second player assigns all the even variables, and they have to do this in turn. This is an adaptive game. If the first player can make this formula true, regardless of how second player is doing in the process, then it's called the first player has a winning strategy. It win the game. Right? So this literally means that whether this particular configuration has a winning strategy for the first player. Right? Because the first player keep on saying, I have a solution, regardless of what you do, then I have another solution, regardless of what you do, eventually I said I win. Right? So this is a multiple round of interactions. Right? And eventually, the verifier also say accept and reject. Accept means that this board game has a winning strategy by the first player. Reject means this board game does not. Right? So in this case, in this interactive proof version, essentially the last verification of this game is in polynomial time. Right? Which means that after you deliver the transcript of communication, then the verifier will say yes or no. That is in polynomial time. The last check is in polynomial time. Just like here, the last verification is in polynomial time. Okay, the verification has to be done in polynomial time. So you can also define soundness and completeness. And this exactly captures whether a board is winnable or not. Right? So how many of you play chess? I'm very bad with it. How many of you like any board game? What board game do you like? There are a lot of beautiful board games, right? They are very intense often, right? So essentially, the whole board game, one of the initial set of problem is basically, I give you a partial game board. Then, suppose you are the player make the next move, and there's a decision problem, whether that player can win. Right? It can win is exactly this statement. That this play, regardless of what the opponents do, it has a play, regardless of what the opponent do, eventually leading to a winner situation. Right? So this actually characterizes P-space. Right? So this means that in this rudimentary interactive way, it actually characterizes P-space. Okay? So this what I'm trying to portray is that you can see interactive proof overall is really showed up not just in human-machine interaction, machine-machine interaction, identification, but also in a variety of other settings, including puzzles, board games, including complexity class, and so on. So this is where, to a larger degree, the interactive notion of proof has always been there. Okay. So what is strict before? Sorry. But what is strict before? Strict before is the strictness of soundness and completeness. That is saying that if you are in the language, you always can convince and accept. If you're not in the language, you cannot convince and accept. Right? So this roughly captures the identification, right? What you want. if you hold your own ID, you should convince or accept of the bank. The bank cannot deny service. So that is your completeness, right? You will hate the ATM machine when you really need the money. You go in there and you try the ATM machine, say sorry, reject. Then you will protest the bank to say this bank system is not good. That's the completeness thing. On the other hand, to a larger degree, the security is the notion of soundness, right? That is, if it's not you, people shouldn't take money out of your bank account. That is soundness, right? So security requires the bank to be sound. Namely, if it's not you, they shouldn't convince the machine. And you want the bank to be complete, because if it is you, you want to get the money, right? So this is the traditional way of NP. It is a traditional way of the most ideal notion of identification. Right? So for a long time, the NP theory has just been there, just like this, right? But identification often gives us a small slack, right? Because if you ask me which soundness or completeness, different people have certain preference. People are supposed to say, I have a bank system. I can't give you 100% guarantee of soundness and completeness. Which one would you like to relax a little bit? I mean, we have to face in life because that's a solution offered. Do you prefer other people taking money off your bank? Or do you prefer occasionally they will deny your service? Which one you guys want?
Occasionally deny us service.
Sacrifice completeness.
I think people usually try to satisfy completeness, right? Usually try to satisfy completeness. But, symmetrically, there's a soundness. Occasionally, people get money. You like that system? Suppose I say, 0.01%, some people will take money out.
If I am the 0.1%
But then you can say, let's buy insurance, right? So that's where the insurance allow you to also, in practice, to talk about compromise between soundness and completeness, right? You can say that you can buy insurance, the bank can buy insurance, right? Because the bank needs to guarantee that the other people don't take your money out. So if the system is the 0.1%, then bank can properly get that insurance. Namely, if people take money out of your bank, what does the bank do? They collect money from insurance and give it to you, right? Put back to your account. This actually is most of the banking scheme, right? Agreed? So if you go to practice, both of this can be sacrificed, right? Because the customer are willing to sacrifice a little bit of completeness, and bank are willing to sacrifice a little bit of soundness, because there's other mechanism to make it self-contained, like insurance, like you said sometimes it's okay. Because sometimes we knew we go to a bank ATM machine, there's no money in that machine, you will be rejected. There's other reason to be rejected too, right? So that's why it can happen sometimes, even from this perspective, right? So you can see from practical perspective, this can all be a little bit compromised, approximated. And what used to be hard for mathematicians is that if you ask them for mathematicians, that in order to solve a problem, would you compromise which? Traditionally, people say, I don't want to compromise anything, right? Because it's hard for mathematicians to try to think about compromisation. And in fact, we talk a lot about Levin's work, which really among the most brilliant mathematicians in the field of computing. And Levin always like to make this statement, which I think absolutely witty. He basically said, in mathematical proofs, there's no approximation. If you're allowed to make one error, you can prove anything. Then he said, here is my proof. You just say define false equal to truth. Then you can prove anything. So you just need one error to prove everything, right? So so you can see, traditionally in theory, it's hard to imagine certain things to be compromised. Right? But the practical setting, it sometimes falls to the hand to say, what if we compromise such a system? Will it allow us to do more? Right? And this actually the common ground where zero-knowledge proof arises to. Okay? So I can define a notion of epsilon soundness, and I can define a notion of delta notion of completeness. Right? So everyone essentially see such system or language can be defined, right? It says that I do these interactions, and if this is not satisfiable, there's absolute chance the machine will say yes, which means people will take money out of your account. And at delta, the approximation of completeness means that even though you play all the rules of trying to prove the system, log on to the system, there's still a small chance the verifier says, sorry, it will reject you. Right? So this is the potentially both set of errors. Right? Okay? Any question up to here? Interactive proof. Okay. So this is basically the landscape of interactive proof. It gives you both P-space and NP to a larger degree into this type of language. And in complexity theory, they also have something called the polynomial hierarchy. That is, allow you to play this game in constant round. That's called polynomial hierarchy. If you want to make a decision like this in constant round, that's called polynomial hierarchy. Okay? PH. So now I would like to introduce this notion of approximation, and more importantly, is we want to introduce the notion of randomness. That is, in these interactions, the provers and the verifiers, either one or both, may have access to random numbers. And so interactive proof and zero-knowledge proof largely are built upon this final combination. It allows you to make some errors, and it allows the prover and the verifier to use randomness to assist them in the protocol. Because once you relax this, suddenly randomness is allowed. Right? Because we are talking about the probability that people take your money. That is a random language. The language about randomness. Right? So when we combine this randomness, remarkably the framework changed. It suddenly allows one to capture certain notion of knowledge. Right? So the combination of randomness and the interactive proof in the sort of this application domain of identification and theoretical schema such as NP, and or called interactive exam, right? So my father went through a Russian system in China. So for 6 years they studied in Harbin in this Russian university. He told me that most of his exam was done orally. So they don't do much written exam, he said, during those days. And oral exam basically are interactive proof, right? Right? You go there, you say something, the professor asks some questions, you say something, professor asks some questions, at the end of the day, professor says you pass. Otherwise, they fail, right? PhD defense is an interactive proof, right? And in some sense, sometimes we do have an approximate soundness completeness, right? Because sometimes, depending on some random event happened, a thesis was postponed and rejected or passed, right? So you can see that interactive proof with noise are very popular, commonly used schema in real life, right? Interval is an interactive proof, right? Because the questions are generated adaptively, right? either ask you a question, you offer answer, they may ask you another question because you answer, and then you have to give another answer. In the end of the day, the interviewer say, you did good. The offer is made or recommended, right? So you can see this, to a larger degree, are very much a practical schema, right? In addition to this theory. Okay, so so in the next hour, I would like to basically offer an example of such interactive proof to prove something that even for certain problem that we don't know whether you can be solved in polynomial time or not, or we don't even know whether you can solve in strictly NP or not, still have an interactive proof. Right? So this gives us a very concrete example to think about. And then next time I will begin to add this notion of knowledge, because we learn so much about distributions. And once you have that distributions, this sense of knowledge can be encoded there. Okay. So since I'm right now right at halfway, maybe we take a 5 minutes break. Then I will, because the second half will just be on this particular problem. Okay. So let's take